So hey everyone, this is Mr. Walsh. I decided what I would do for you guys is actually record my voice over these PowerPoints and post it. So just like in class, I would be explaining PowerPoints, drawing things on the board. I have a little whiteboard I'm going to use. We'll kind of just pretend that this is that we're all together for class. Okay? So it's really unfortunate, but VSEPR is sometimes a tricky concept for students, and me not being able to do this in person may be a little more challenging, but we will do the absolute best that we can. Okay? So we're going to start talking about molecular geometry and bonding theories, but before we do that, I just want to go back to the drawing board for a sec and do this. So we can have single bonds. Okay. So if this is methane, all right, this is a carbon with 4 single bonds on it. We can also have, here, double bonds. Okay, and we can also have, that's an H, sorry, that's not great. You can also have triple bonds. Okay? So in a single bond, right, you just have one pair of electrons connecting the 2 atoms. In double bonds, you have 4. These are my electrons. And in a triple bond, you have 3. Okay? So keep this in mind for molecular geometry, because this will come into play a little bit there. All right? So molecular geometry is 3-dimensional, right? So the board that I just showed you guys, the molecules are flat. It's letters on a board. But in real life, these atoms exist 3-dimensional. They exist with volume, length, width, height. They have depth. Just like your cell phone that you guys use, your textbooks, 3-dimensional. So we need to take this into account 3-dimensionally for these molecules. Now, why didn't we do this with ionic bonds? And the answer is because, if you remember, I very briefly talking about ionic bonds having crystal structures. They're crystalline. And that was their geometry. And they have their own set of rules. Like most high schools don't spend a lot of time on those crystal structures because it's not the most important thing. Okay, VSEPR, this geometry is much more interesting, and it's a little bit more fun, kind of. I don't know, maybe. I think it is. Okay. So we can predict our geometry using both Lewis structures, which you guys should know how to do by now, and VSEPR. And VSEPR actually is an acronym. Okay, VSEPR stands for this is VSEPR. It's valence, shell, electron, pair, repulsion. Okay. So valence, shell, electron, pair, repulsion. So what does that mean? Well, that means we're talking about our valence shells. So our electrons in the outermost energy level, and we're talking about how they repel each other. Because you guys remember and know that electrons are all negatively charged and they repel each other. They don't like each other, right? So, VSEPR takes that into account and says, well, how can we apply this repulsion to find geometry? All right, so you saw this. So, you'll see this a lot, this A, B, X. These are just placeholders, just like in math, right? You'd have 2X or 2Y. So we're just saying this could be any combination of atoms, okay? And we'll show practical examples dealing with real atoms. So A will be the central atom, B will be the atoms surrounding it, and X is usually a number from 1 to 6. You won't see anything more than that usually, because at that point you'd have very special rules that we won't deal with. Okay? So, an example. If you have an AB1, so you have an A, you have your B, and you only have 1. They're linear, okay? They're going to be just in a straight line. There's no reason for them to repel. This is as far away from each other as they can possibly get. I go back to my drawing board for you guys here. If I clear the board, all right, so if we have we have our B, right? If I move this, let's say I want to move this guy here closer. Well, I can't really do that because what's happening is we have lone pairs on these guys, and so if I move him closer, right, these lone pairs are now in a greater proximity than if they were over here. Now remember, this is a drawing board on a computer, so these are not to scale, these are not accurate in any way, but you see, if I color this in just because I can, the fact that they are linear means these electrons are as far away from each other as they can possibly be. You go in any direction, left or right, you're going to put them closer, and they don't want that. So AB1 will be linear. Okay. AB2. So now we have another central atom. Will either be, or now we have another atom outside. Will either be linear or bent. Okay? And this will have to do with whether or not you have lone pairs on the central atom. I'll show you examples of this and you will see what this looks like. If we go AB3, let's just say we add another one. You have planar, pyramidal, or T-shaped. So what's the difference? Again, these come down to lone pairs because they both have 1, 2, 3, 4 atoms. 1, 2, 3, 4 atoms. 1, 2, 3, 4 atoms total. Now, I'm not too concerned with you knowing this guy. Okay, that guy really doesn't play that much of a role for our purposes, but these two, what's the difference? Their arrangement, right? And so what do you think it's going to come down to? Lone pairs. Lone pairs of electrons, or what we call non-bonding pairs of electrons. All right. So I already told you this, but they give it to you again, valence shell electron pair repulsion. All right, this is kind of, so, essentially this is what I've said. Electron pairs move as far apart as possible to minimize repulsion. In other words, they want to be away from each other as much as is humanly possible. An electron domain or an electron cloud, that would be either a pair of electrons or any type of bond at all. Okay? So if I go back to my drawing for you guys, okay, if I clear the board, if I take molecule, let's do one like this. Let's just say we have this. Okay, we got some lone pairs. And we would have one, two, three, four, five. 5 domains. 5 electron domains. Okay? So we count the pairs of electrons as 1, a bond is 1, and so on. So it'd be 1, 2, 3, 4, 5. Now if we have a double bond, all right, if we have a double or even a triple bond, those still each count as 1, okay, because it's just a location of electrons. So this would only have one domain, okay? So that's what we mean by electron domains. We mean locations or clouds of electrons. So from Lewis structure, let me do this. Sorry about some of this. You can do your electron domain geometry and your molecular geometry. There's a little bit of a difference, which we'll talk about. So, let me just get all this up for you guys. So, step number 1, draw your Lewis structure. So if I give you a molecule, you can draw your Lewis structure. Step number 2, count the number of electron domains on the central atom. So we don't care what's going on here or here. We care about the central atom. So we have one on the carbon and another one on the carbon. Remember I said 3 bonds is 1. So we have 2 on this one. And that is your electron domain geometry. So this nitrogen has 3. 1, 2, and 3. Okay, xenon here, 5. 1, 2, 3, 4, 5. Okay? So that's electron domains. You just count, is there a pair of electrons? Is there some number of bonds? That is electron domain geometry. So unfortunately, the program I'm using only gives 15 minutes per video. So what I want you guys to do, I want you to go back over this, look at my drawings, look at these. Even if you don't have my voice going, make sure you understand how we got to this point. Okay? I'll be emailing or posting other instructions in Google Classroom about homework and things. So this is going to be video 1. I'll probably do another one soon. All right.